with recycle, but ideally for a chemical reaction or for multiple chemical reaction, because recycle has meaning whenever there is a reaction and reaction doesn't go to completion, and you have to therefore send back feedback part of the product stream, or rather the unconverted product, whatever is in the unconverted reactants which are in the product stream, and you send them back to process it in the units, right? So that's exactly what we wanted to do. But however, we got stuck in that non-reactive problem, and while we were solving, you said that for K2CrO4, one of you said it will have 1,500 kg per hour, or whatever the units were, I don't remember, kg per hour, and I immediately disputed that, saying that's impossible, because that was not possible, because the basis was 4,500 kg of K2CrO4. Total feed was 4,500 kilogram per hour, and of that 1/3 was potassium chromate. So that itself gives me 1,500. And we know that the crystallizer doesn't give you 100% crystals. So of course, it could not be 1,500 as Dhwani and somebody else told. So the question was, how do we solve it? We should quickly recapitulate that before we go to the actual thing, which is chemical reactions, right? I mean, and the next 2 weeks we'll be doing mass balance with chemical reactions, and we want to go to recycle problems with chemical reactions, maybe even with multiple chemical reactions. I don't know. Let us see. Anyway, so to go back to that, to recapitulate that, so that's how I knew that 1,500 could not be the answer, because the total mass that the crystallizer gives you, I mean, there was some solution or liquor that was entrained in it. So that sum total, and we knew that of that sum total, only 95% was crystal and 5% was solution. So basically that gave me a ratio of if the solution was S and the crystal was C, then S was only 5% of C plus S. So that gave me a relationship between them. And I can also do the overall balance. If Q was the evaporator load, then the sum of the crystals plus the solution plus the evaporator Q load has to equal 4,500, because as you said, those are the only streams that intersect the overall mass balance. So that gave me 3 unknowns. And then I said, still we need one more equation. So I said, if you can do an overall balance, you can also do an overall water or overall potassium chromate balance. And that is what I was trying, because that is how I knew that 1,500 was wrong, because 4,500 times 33 or 1 times 1/3, that's 1,500 kilogram potassium chromate per hour. That has to equal the crystals, because that's pure potassium chromate, so C, plus it has to equal the solution mother liquor S into 0.3636, because that's the composition of the solid potassium chromate in the mother liquor. So you get the other equation from an overall balance on the potassium chromate, that 1/3 into 4,500 is equal to C, which is the crystals, plus something. And that's why it will be less than 1,500, plus 0.3636 into S. So, and you know that one is 5% of the other, so you have to solve for the crystal, so you will get a number less than 1,500. And once you know the C and the S, you can do the overall balance, and you know the heat load, I mean the evaporator load Q. So you know all of those 3, but that still doesn't give you the recycle ratio R, right? I mean, or rather, that doesn't give you the recycle, how much kg per hour you recycle. The ratio you will find out later. So for that, you have to do a balance on either the about the evaporator or about the crystallizer. So, oops, maybe I should share that slide. So doing it about evaporator is possible, but then I do not know the combined feed to the evaporator. I do not have the combined feed to the evaporator, so that's an additional unknown. While if I do it on the crystallizer, I know that some F is going into the crystallizer, and I know the amount of crystal C that you already found out from the overall balance. You know the amount of mother liquor S that you know, and that plus R has to be equal to the what you're feeding into the crystallizer. Where is exactly? So whatever you are feeding into the crystallizer must equal the recycle stream plus the solid crystals plus the solution in equilibrium with that. So you know both S, capital S and capital C, which was the solution and the crystal from the overall balance. So R and F fed into the crystallizer are unknown. Now do a potassium chromate balance or a water balance from the crystallizer. So if F went into the crystallizer, of that 49.4% was K2CrO4. So you know that 0.494 times that is the amount potassium chromate. You know that the crystal that was produced, which was 95%, that's pure potassium chromate. Whatever number you got, little less than 1500, whatever 1400 something. So that plus basically you had the solution that also contained 36.36. So whatever capital S was when you solved it, that times 0.3636, plus there is potassium chromate in the recycle stream. So R was the recycle streams in kg per hour. So R into 0.3636. So that gives me another equation. So 0.494 into F into of crystallizer is whatever you got, capital C, little less than 1500, plus 0.3636 into the solution, capital S, plus R into 0.3636. So that is there. And of course, you have the overall balance that F was equal to R plus C plus S. So you can solve them simultaneously and you will get all the variables. But the problem now is we have to actually conduct chemical reactions in this. That was what was where we were heading to, and what I wanted to do last time. The thing is, when we discuss chemical reaction, we have to worry about the concept of chemical kinetics, which you already know, but we have to nonetheless skim through it. The concept of limiting and excess reactants, because as you know, suppose you are combusting something, you will have oxygen, nitrogen, then say, let us say the methane or whatever you have, the alkane or alkene, or so nothing goes to 100%, and you will have also, depending on what you fed in, not all of the reactants will get completely consumed. So basically, one reactant is called limiting because when you wrote the stoichiometric equation for that reaction, you know, so many 1 mole of this methane gets combusted by 2 moles of oxygen. So you know, if I fed in 1 mole of methane, 2 moles of oxygen, etc., etc. And now the limiting reactant is the one which completely gets consumed, and every other reactant that you have fed in, you fed in much more than was needed to do complete combustion based on that stoichiometric equation, the reaction equation, right? So those are excess reactants. And always when we define conversion, we base it on the limiting reactant, that is the one that was not in excess, right? So let us just look at these concepts again. So basically, this is the point. So the reactant that would get completely consumed is what I said here. Slide says reactant that would run out, okay, that would be completely consumed if the reactant proceeded to completion, right? That is the limiting. Now every other reactant would be in excess. So those are excess reactants. So the italics one says reactant is limiting if it is present in less than its stoichiometric proportion relative to every other reactant. That's correct. So you have the chemical equation, the reaction stoichiometric equation, and basically, you know, 1 mole reacts with 2 moles, and now if every thing that is in excess, if you got that limiting reactant to get completely consumed and you finish the 1 mole of the methane, and you fed in more than say 2 moles of, assuming 1:2 ratio to oxygen, and you fed more than 2 moles, then whatever remains, the number of moles after reaction is in excess. So you can always find how many, suppose you fed 3 moles, then 1 mole of oxygen will remain in excess. So of course, as you say, all reactants could be in stoichiometric. That is, you put exactly as per the mole ratio, as per the complete combustion reaction equation. But that is never done in actual practice. Okay, it never is done. So that every is in exact, I mean, everything gets completely consumed. It never happens in actual practice. Okay, so we have to always, before we do any calculation, we have to identify which reactant is limiting and which are the excess reactants, because our conversion, the fractional conversion F, is always based on the limiting reactant. So moles of limiting reactant reacted upon moles of limiting reactant fed. So many times the conversion, maybe you fed in methane, but maybe everything did not get, I mean, you fed in something and the reaction didn't go to completion. So then you will have how many moles you reacted, how many moles you fed. That gives you your extent of conversion. I think you know all of these things. So we should try and practice some problem. Of course, all of these we want to finally do one reaction, multiple reactions, and then do that in the context of a recycle. That is what we want to do in the next 2 weeks. So first, just take this and we can discuss whatever is required in the context of an actual question. So please try and look at this. So all of those concepts of limiting reactant, excess reactant, we can identify based on an actual example in which acrylonitrile and ammonia and oxygen are reacted. Or rather, acrylonitrile is produced. So he has given you a basis and you have to find out which reactant is not in excess. And also he asks all the other reactants, what percentage excess is there? And then he adds a third stipulation that the 100% conversion hota nahi hai. In other words, F, small f is 30% or 0.3. Now how many moles are there in the exit flue gas of all the components? So you have to worry about how much reacted and how much was left and what was in excess, and finally based on that 30% conversion, how much of the products, acrylonitrile and water was produced and how much you fed in, and then the decrease, the diminution of that two, subtraction of that two has to come in the exit flue gas. So we are starting with a single reaction, okay, and ultimately, of course, we want to go to multiple reactions because then things become interesting for us. We can talk of selectivity, right? Very important concept in catalysis and reaction engineering, etc. And you can have multiple pathways by which, let us say, in this case, propylene is reacting. So here we are just taking a simple example of a single reaction to understand limiting reactant and excess reactant, which I think you already know from your JEE chemistry. So again, try and represent all of this information in a flow sheet, a flow diagram. Okay, this is again simpler because it's only a single unit again. Just that this is our first time we are looking at a simple chemical reaction. Is the question clear?
Yes, sir.
Let us try to solve. Let us try to solve it exactly, because I don't want to spend too much time on limiting excess reactants because we have to move on. But today is the only class on this because I think you should know these concepts. So why not try and solve this exactly, and then we can go on to more interesting mass balance with chemical reactions, multiple reactions. But everywhere you will have to find out what is the fractional conversion. And once the fractional conversion less than 1, there will be a lot of unreacted species, chemical species. So you have to account for all of those things. And this we are still doing mass balance. Imagine if you have to do energy balance, which we will do in November, we need to also worry about the enthalpy or energy that these streams carry with them. So obviously, if we don't do the mass balance correctly, how will we ever get the energy balance right? So you can take 100 moles as the basis and then find out what are all the input stream contains what all species.
So you'll have like if
10
100 mole is
moles
the
of,
basis, 10 moles of propylene, 12
correct,
moles of ammonia,
right,
and 78 moles of air. So that will be 21% will be oxygen out of that.
correct. If you
That'd
are
be
short of time,
16.38.
you can take it 2080 if it is so. Okay, yeah, correct. So you know the input. Now identify all the streams in the output. I mean, there's only one stream. Identify all the components in that stream. Sorry,
So it'll have
right,
all the components, right? Like
correct.
propylene, ammonia, oxygen, then
Nitrogen also.
nitrogen as well, and then the
Product,
products, water and
correct.
the other product.
All of them are there. Very nice. So now find out how from the stoichiometric reactions find out how much of these uh, oxygen is consumed and how much of ammonia is consumed. See, ammonia, 1 mole of ammonia is reacting with 1 mole of C3H6.
So since it says 30% of the limiting reactant is converted, and we can find like the limiting reactant is propylene.
Right, but first find the limiting reactant. Go to the 30%. I mean, for instance,
Yeah, sir,
one
it's propylene, right? Because we have 10 equivalents of propylene, 12 equivalents
correct,
of ammonia, and 16.38 moles of oxygen. That is 10.92 equivalents. Equivalents come like if you multiply it by 2 by 3,
right,
because you need 3 by 2 per mole of propylene.
right, 1.5. Yeah, O2 by C3H6 stoichiometric is 1.5.
Yeah.
So those can't be limiting because NH3 upon C3H6 is only 1:1 as per the reaction. Ammonia upon C3H6 is 1.2 because you only told me 12 upon 10, no?
Yeah.
12 moles,
Yeah.
10 moles. So that cannot be limiting either. So ammonia cannot be limiting.
Yeah.
And you just now told me oxygen cannot be limiting. So
Yeah. So
you're
like
right.
propylene is limiting,
Propylene is limiting.
and we have like 30% of it is converted. So that's like 3 moles out of 10 moles is converted into the product.
Right. But the first find out how much of ammonia and oxygen are in excess.
So 12 moles of ammonia and 0.92 equivalents of oxygen, that is 0.92 into 3.2 or 3 by 2 moles.
We have to find the percentage excess. That's what he
Okay,
says.
okay, okay.
Ammonia, how much percentage in excess? Because you have now identified propylene as the limiting reactant. So that will get consumed. You know how much of ammonia you fed in, and you know from the reaction how much you would feed, how much ammonia will be converted. So you know how much remains.
Yeah. So for finding excess percent, we don't have to consider the fractional conversion, right?
No,
Okay.
that's what I meant. That's why I said don't jump the gun. First do the percentage excess, and then only we worry about fractional conversion. So you can say that percentage excess of ammonia is how much ammonia you fed minus how much ammonia reacted if it had followed this stoichiometric conversion equation that you have in the problem, divided by how much of the stoichiometric thing was the same number, that is into 100 is the percentage excess. So moles of ammonia fed minus moles reacted stoichiometrically divided by moles of ammonia reacted as per the stoichiometric balance of this equation into 100, that is the percentage excess of ammonia. Similarly, you can find for oxygen. So how much ammonia was fed?
So 12 moles and
12 moles.
10,
How much
10
ammonia
moles.
reacted? So the
So 10
difference was
moles.
2 moles. So the
Yeah.
numerator is 2 moles. This you divide always to find the percentage. We have to divide by the stoichiometric number. How much is that?
So 10.
10.
So 20%.
100%. So how many percent excess you got? 20.
20%.
So that's for ammonia. Now do the same with oxygen.
So oxygen will be 1.38 moles will be in excess and 15 moles will be consumed. So 1.38 by 15 into 100, that's 9.2.
10, little less than 10%. That's right. Because that's right. Because 16.4 minus 15 upon 15. Yes. So you will get about a little less than 10% excess of oxygen. So this is what he has asked. Now you figure out how much acrylonitrile is produced, formed. Now you have to use conversion.
So it'll be 3 moles itself, right? Because we have 30% of the like fractional conversion is 30% for the limiting reagent, and
Right,
the limiting reagent is 10 moles. So 3 moles is converted, so 3 moles of acrylonitrile is formed and 9 moles of water.
right. Because for every 10 moles of C3H6 that is fed, reaction conversion is only 30%, because only 0.3 moles are reacting per mole of fed. So you will get 10 into 0.3, 3 moles of C3H6 have reacted. So as you have correctly said, for 3 moles of C3H6 reacted, you form 3 moles of acrylonitrile. So he asks you per mole of ammonia, you will get 3 moles upon 12. That is your answer actually. Suppose I ask you how many moles of acrylonitrile is produced per mole of ammonia. So that number is 3 upon 12. Or 0.25 moles product acrylonitrile per mole of fed of ammonia is 0.25. So that's the kind of ratio you are getting for the 30% conversion of the limiting reactant. So essentially, this was the flow sheet. You have now identified everything in the output. How much of the product was there, how much of the unconverted excess reactants went into that stream, etc. And so you can find any fraction, anything, once you know the moles of C3H6, ammonia, oxygen, nitrogen, and product, acrylonitrile and water. Now, all of this is only for a single reaction. But I don't think there is any process where, any chemical process where the desired product is just going to be produced by a single reaction. Certainly in a combustion process that's quite impossible. Even in any dehydrogenation process it's not true. biological processes may be more specific, but there is always side reactions. So your substrates can combine in more than one way. The product itself, if you don't separate it or remove it, it may combine with some other species and form something less desirable. That is also possible, depending on the process. So now suppose I had multiple reactions. Let us say, ethylene is being produced by dehydrogenation of ethane. So ethylene is the desired product, but all of these reactions have so many recombination reactions also. And we also produce methane and we produce C3H6, and there are all of these recombination reaction of ethylene and ethane, which produces propylene. So there will be C3H6, CH4, which are all side products. And they are not products. I would say they may be undesired products. So they will lower the yield. That's the variable. That's the nomenclature I was looking. That's the word I was looking for. So you already now know what conversion is. Now what we have to discuss is how do we look at yield. I mean, this comes in when you have more than one reaction. As I said in the example, ethane is going to ethylene plus H2. So it is your desired product, but ethane can also form methane by combining with hydrogen, and it can also have recombination reaction and form other products, other by or side products which you may not want. For instance, you may want conditions where the desired product ethylene is maximized and all the byproducts or impurities such as ethane and C3H6 are minimized. So in this situation, if I want to find out what is the yield that this combined reaction system is producing based on how much you fed to the unit, how should we define that yield is what I want you to think on. See, for a single reaction, it was very simple. All you have to do is look at the stoichiometry, take the basis given or assumed at 100 moles per hour or what have you, and then based on the thing you will find if this limiting this 1:1, 1:2, so you will calculate all the other things based on that, find out which one gets consumed and remaining were excess, and then you are given a fractional conversion of the limiting reactant, and you could find out every composition and then every ratio and every weight percent, mass percent, mole percent, anything. But when I have side reactions, I have a desired product, and I also have all these undesired side products. Then how should I define? I mean, I don't want to use the word conversion because then I will confuse it with the earlier one, because that conversion we define based on the limiting reactant. Now, how should we define yield for, say, this multi reactions are taking place, and we know which is the desired product, we know what are the undesired products. Because very often we have to find out what is this yield, and that's a very important number for mass balance with chemical reactions, multiple reactions. There is no one way to do this, but what is the most logical way and what is most commonly used in at least commercial industry, chemical processing industry? You always measure how much was fed. So I mean that is the fresh feed. Okay, I mean if there is a recycle stream, we said there are two feeds. No, there is the fresh feed and then the recycle stream gets combined and forms a combined feed. So normally You base everything on the fresh feed. So if I have to define a yield based on fresh feed, what should I do? This is the question I want you to think on. Of course, you can define yield based on other concepts also, but normally we, in the continuous process, we are interested in how much fresh feed we fed into the reactor, right? Or the train of reactor separator units. This whole thing, if there was a single reaction, the concept of yield was, conversion was sufficient, but now we need to worry about the desired thing also and the undesired byproducts or impurities. How much does the desired reaction dominate or take precedence over the side reaction, which may be our competing reactions, and ideally we would like, of course, to choose conditions and minimize that, but they are always going to be there. So how should I define a yield, and how should I compare yields under different process conditions? It's an important number for us. Now you can, as I said, normally we want to look at yield based on how much fresh feed you fed into the system. Of course, I can look at yield based on how much was the combined feed, if it was a recycle, or how much of the reactant was consumed by the reactor. That also I can look at. But suppose I were to base it on the fresh feed, or based on overall material balance feed, and we already know how to do that overall balance because we drew the boundary about the entire combined units, the outer boundary, let's call it. So then what is the yield? How would you, can anyone try?
So can you repeat the question? I didn't understand.
Yeah. Okay, other words. Well, basically, the concept of conversion, you already now saw how to do that for the single reaction. But when there are more than one reaction, conversion is not sufficient for us. We have to find out how much the reaction that we want is predominating over the side reactions which for us are undesirable, because now there are more than one reaction. So those other reactions are also consuming reactants, yet our product is only one out of those n reactions. It's only given by one of those n reactions, the product. The desired product is only given by one reaction. So how do I look at this yield? Okay, look at yield in any way you want. I don't care. I mean, I said, look, you can look at it as overall balance. You can look at it as what is fed to the reactor. Both are possible. Any yield. How would you define it? Was my big question. Obviously, you want to maximize this yield, right? Ideally, you want to maximize two things, yield and selectivity. So how should we define yield and how should we define selectivity?
Sir, I guess yield should be like theoretically how much product should have been formed and actually how much formed. So like we divide both of them.
Okay, yield is never like that. What we did limiting, it's never based on what is actually happens divided by theoretical. It's not like that. Yield is always based on what is actual. So that does not work. Yield is always based on actually how much of the desired product is formed. Okay. Not that how much should have been formed and all doesn't come in. So that type of ratio or percentage or number doesn't help much. So, okay, the answer to it is yield is always, you look at, there are undesired product, desired product. So you look at how many moles of the desired product is formed per unit mole of the limiting reactant that is consumed. You already know how to identify limiting reactant. You just did it. Now you have many more reactions taking place. So now this limiting reactant will be consumed by many reactions. Let it be consumed. You find how many moles of that limiting reactant was consumed by all the reactions. And of the moles of limiting reactants which are fed or consumed, I say fed or consumed because if I look at the overall mass balance, I am only feeding it in. I don't know how many are consumed because as you have correctly said, it may not be 100% conversion. So whatever is the number of moles of the limiting reactant which is fed or consumed, out of that, how many moles of the product, that is the desired product, I should say, got formed, is a measure of the yield. So please take down. I will compile the definition. If you base it on overall material balance, then the yield based on the overall feed is moles of the desired product that are produced per mole of limiting reactant which is fed to the composite system. So okay, next time we will summarize this. But as I said many times, this is a very gross number. How much you fed, how much you got. But many times, if there is a reactive process, you are more interested in how many moles of the remitting reactant were actually consumed by the reaction. That is after taking account the conversion factor. So then you get a yield which is based on the consumption of the limiting reactant. So that you can call how much moles of product was formed per mole of remitting reactant which was consumed. That's a different number. So these are very common ways of defining yield. So then you can also now define selectivity because you know there is a reaction which produces the desired product and there are multiple reactions which produce undesired product. So that ratio will give me a measure of selectivity, isn't it? So how many moles of the desired product are formed and how many moles of undesired product are formed. And we want to maximize this number. So that is a measure of selectivity. So let us look at all these concepts for a multiple reaction system, and then you can, just as you calculate it for conversion and excess and all of that, you can now calculate all of these with a certain fractional conversion which is not 1. You can also calculate yield, overall yield based on feed, overall yield based on consumption of limiting reactant, then also selectivity. All of those things we can complete tomorrow, and then we are ready to take up mass balance problems with chemical reaction, multiple chemical reactions, including recycle. That would be what we want to do by end of October. We want to reach there. Okay. This will be what, and then we will worry about then November. We want to go into energy balance. All right. So let us define these. You can try your hand at measuring, calculating for a particular multiple reaction system, yield, selectivity, etc. Then we can do some more and more complex problems on mass balance with multiple reactions. Okay, thank you.
Thank you, sir.